Here we are in topic 19, and what we're going to be talking about are parametric curves, which are a kind of generalization of the curves that you might have seen as Cartesian curves of the form y equals f of x, or polar curves of the form r as a function of theta. These curves generalize all of those and expand the universe of the kinds of curves we can represent mathematically to practically anything you can think of. Spirals, loops, ellipses, you name it. They all can be represented parametrically. So let's get started. Let's think about t, little t, as standing for time. For example, t equals 0 means time 0. And let's pretend, in fact, over here in this illustration, by the way, t is at 0. And let's pretend we have a particle sitting somewhere whose coordinates are functions of time, depend on time. In other words, this particle is going to move around as time changes. At time 0, it's sitting over there on the x-axis. I know this x-axis looks rather messy, but ignore that. Okay? So it's sitting on the x-axis around time t at point 3, more or less, right? X equals 3, and y equals 0. As time changes, and I'm going to animate that by moving the slider here. As time changes, as we increase from time 0, this particle is going to move around, and by moving around, it kind of traces out a curve. And that is what a parametric curve is. So let's look at what this particle will do. So I'm going to move it, increase time, and as time increases, notice the particle goes looping up the y-axis. So what's happening is that the position p is a function of time, meaning that the x and the y coordinates are functions of time t, which is why they're written as x of t and y of t. And as time goes on, the position changes, and it goes looping around the y-axis in this particular case, and that is a parametric curve. Now, I'm not going to give you a formula for this particular curve, but it's actually quite a simple one. What I am going to do is write down the generalities of what we've been saying over here. So imagine, as I said, a particle moving around in the xy plane, then its x and y coordinates vary with time t, so they're functions of t, which is why I've written x equals x of t, meaning x is a function of t, it's not just a number. And the same goes for y. And the curve that gets traced out is called a parametric curve. And specifically, the value of t that I've been using lies in some interval starting at 0, and in this case going to 40. So the value of t lies in the interval from 0 to 40, the closed interval in this particular case. And in general, t is going to belong to some possibly infinite interval. Let's call that interval I. So there's three things happening. X is a function of t, y is a function of t, and t is restricted to be in some interval. That may be no restriction at all. We could choose the interval to be the whole real line, in which case t would be any real number. In this illustrated example, t is between 0 and 40. Goes as far as 40, all right? Not too terrible, okay? Mathematically, by the way, the actual curve that's traced out is the set of all points, x of t, y of t. Where I see there's a parenthesis missing, so let me add it in there. There it is. The set of all points, x of t, y of t, where t is in the interval, as t varies in this case from 0 to 40. So we could have written t in I like this as set theory, or t is between 0 and 40 in this particular case. So I think rather than looking at the general case, we should look at examples. And I think the simplest example to look at would be, yes, a straight line. In fact, a straight line segment from one point to another. So what I'm going to do is try to come up with a formula for that. So in this case, I have my 2 points sitting over here. Here's P plotted at -2, 3, and here is the point Q at 4, 2. And I want this line, as t goes from 0 to 1, I've just arbitrarily decided at t equals 0, it should be at P. And at t equals 1, it should be at Q. I think that's a kind of a logical choice, don't you? So, for example, t equals a half, it should be exactly midway between P and Q. In other words, as time goes on, it moves at a fixed velocity from the point P to the point Q. Now, how do we parameterize it? How do I come up with the equations for x of t and y of t to make this happen? How did I work? How did I do this? What's going on here? And that's what we need to decide. So, rather than looking at this very specific example, let's look at the general case. Let's take a general point P and a general point Q. And in other words, give them coordinates that are not specific numbers, but call them x1, y1, and x2, y2 as follows. So we have P in the general case would be x1, y1, and Q would be the point x2, y2. And we want to think of a particle moving from P to Q along a straight line, as illustrated, with uniform speed, just as I mentioned. Okay, so it's going to move from the first particle to the second particle at a uniform speed as time goes on. So if I move this slider at a fixed speed, then my particle will move at a fixed speed as well. If t equals 1 represents 1 second, then the particle will take 1 second to go from P to Q. So at half a second, it will be midway between them, and then at 1 second, it will be at Q. So it'll be roughly like this. That was about a second, right? That's what I want to do, except I want the general case as illustrated here. And as I said, at time t equals 0, it's got to be at P. And at time t equals 1, it has to be at Q. So my question now is, well, how do I figure out where it is at time t? So let's be a little more specific. And let's ask this question. Where is it at time t equals 1/3? Very specific, right? T equals 1/3, it should be about 1/3 of the way along from P to Q. So what I'm going to do is draw a kind of general figure that illustrates that. So it should be 1/3 of the way along, as I said, and here is the kind of figure that should illustrate where it is in this very general case. So P and Q are not in the same positions as they are in this drawing. They're kind of in a general position. The x-coordinate of P is now x1, and the x-coordinate of Q is x2. I've not put in the y-coordinates because I don't want to clutter this picture up. The y-coordinates would be on the y-axis. At time t equals 1/3, it should be 1/3 of the way along, about there, right? And let's look at the projections of these line segments on the x-axis. In other words, P projects down to x1. At time t equals 1/3, it projects down to this point that's not labeled, and then at time q, it projects down to x2. So this length with the arrows should be 1/3 of the total length. The reason is that this triangle, think of a triangle here where this is the hypotenuse, and then I can have an imaginary adjacent side parallel to the x-axis, but starting at P. Then these lengths at the bottom are just the hypotenuse times cosine of the angle. And so if I have 1/3 of the length, I'm going to get 1/3 of the answer. If I have the whole length, I'll get the whole answer. And all I'm trying to say is that because this length is 1/3 of the total length, it follows that the projected length is 1/3 of the total length, using a bit of trig cosines. So all I have to do is figure out what the x-coordinate is of that point, which is 1/3 of the way from x1 to x2. Now, the total distance from x1 to x2 is the difference. It's just x2 minus x1, right? And so this 1/3 of that distance would be 1/3 of x2 minus x1. That's the length of this little segment over here. Add that to x1 and you get the x-coordinate of this point that I'm interested in. So at time t equals 1/3, the x-coordinate would be x1 plus 1/3 of the difference. And good grief, I've just come up with a formula for the x-coordinate at time t equals 1/3, haven't I? That's kind of nice, so let's formalize that and make it official. At time t equals 1/3, x is x1 plus 1/3 of the difference. And similarly, if you do everything on the y-axis, the same picture just projected onto the y-axis, y1 will be 1/3 of y will be y1 plus 1/3 of the difference of the y-coordinates. So now can you say what's going to happen at time t if I don't tell you it's 1/3? Ah, simple. You just replace 1/3 here and there by the general time t. So we're going to get a formula for the line segment that I'm after. That's how I got this one on the right. And if we do that, we get, for general time t, we just take this very formula and just replace 1/3 by t, as I mentioned. So here's the parametric equations, they called, of straight line segment from P to Q. Given any 2 points P and Q, just put the coordinates of P down first, x1, y1, then put some plus signs, plus plus, then put some t's, t, t, and then x2 minus x1 here, and y2 minus y1 there. And t goes from 0 to 1 inclusive. So when t equals 0, you're at the first point. When t equals 1, you're at the second point. Simple as that. So this works for any set of points, and that is how I got this line to get drawn in GeoGebra, right? So this does example A in the notes, and also example B, which is the general case. So if you look at your notes, you'll see that we've done example A and also example B at once. Well, example A, you just put in, I guess we haven't done example A specifically. We haven't actually put in the numbers. So in this particular case, let's finish example A. Finishing example A. And I'd like to see what I just typed come up. Right, finishing example A. I'm not sure what that is. Let's just see what that is. It said the straight line segment in general. Okay, let's finish example A. If I can get that right, it'll be, there we go. All I do is take these equations. What I'm going to do is just copy them and paste them. These equations that are sitting over there, and then just put in the values. Now, example A had this very specific, it seems to have vanished over there, there it is, very specific P and Q. So x1 is -2, and x2 is 3. So all I have to do is substitute for x1 and x2. So x1, I'm going to put in -2. And there it is, -2, right? And x1 again is -2 in the right-hand piece of the formula, so I'll put that in parentheses. x2 is 4. So x2 is 4. So put that in. And now we have the first equation, which we can just, I guess, simplify. So that would equal -2. How many t's are there? Well, there's -4 minus -2, which is 6t. So I could write that as -2 plus 6t. What about the y coordinates? Well, I have to substitute for y1 and y2. y1 is 3 and y2 is 2. So y1 would be 3. So I put in a 3 for y1 in both places. And for y2, I put in a 2. So that's a 2. Okay, and then simplify that. And so that equals 3 plus just 1 times t, or t. Actually, negative 1 times t. What am I saying? Minus t. End of story. We have now parametrized example A. And t goes from 0 to 1. So let's move to example C, which is, what about the infinite line? Not just the line segment that starts at this point and ends at that point, but what about the infinite line? Infinite line. That means we're going all the way from the left, and then it'll keep going all the way through on the right. So can you guess how you parameterize that? I think you might have guessed it, right? Namely, simply lift the restriction on t. Don't let t stop at 1, let it go on, and then that line should just continue moving to the right. Don't stop t at 0 on the left, let it go on to negative infinity, and that line should extend to the left as well. So let's look at an example of that in action here. Now what has happened here to this picture is that t is allowed to go from negative values. As t comes in from negative values, see my point's kind of moving in. For some reason, it's not tracing out a line as it should be. Well, imagine that it was. And now it decides to pick up the line and keep going forever. So for negative values of t, it would be to the left of p. That's not shown in this drawing, but you can just extend the line yourself manually, right? At time t equals 0, it's still at p. At time t equals 1, it's still at q. And then at time t equals 2, it's, guess where? It will be, if this goes from 0 here to 1 there, at time t equals 2, it will be the same distance to the right of q, because it's moving at a fixed speed of 1, I guess, x unit per second. Interesting. So the line through P and Q has exactly the same set of equations. Namely, I can just take this box over here, copy it, and paste it, and just delete some things. So it's now not a segment anymore, but an infinite line. And let me do that. So I'm going to change the word segment to just line. And instead of from P to Q, I'll say the line through P and Q, as illustrated on the right here. And that line has the exact same parametric equations, except this time t goes from minus infinity, so it's going to be less than, and it's going to be a minus infinity on the left, and it's going to go to plus infinity on the right, so it'll be less than plus infinity on the right. And there is the infinite line, same equations. So I'm not going to go through an example again. You just lift the restriction on time t. No other change. Okay, time to look at a new example that's very different. In fact, let's try, I kind of made a claim earlier that if you take any Cartesian curve whatsoever, you can, what we're doing here generalizes that concept as well. So what I'm going to do is erase everything about parametric lines, straight lines. If you don't mind, pause the video as usual and put up example D. So example D is a generalized example again that says, okay, if you have any Cartesian curve whatsoever, f, we want the graph. We want to parameterize the graph of that function. And so once again, we're going to look at a specific example, and we're going to look at what example should we look. We've got to pick an example, but by the way, the domain of this function is going to be an interval here, right? And the codomain, the target is going to be the real numbers. So here's one. Let's take, not that one, because I've just said that, so let's try this. Example, f of x equals x squared. And what domain should I use? Well, just to be naughty, I will use only half the real line as the domain, only the non-negative real numbers. And so the graph of this, as you should know by now, is not the entire parabola, y equals x squared, but it's half of a parabola. So this is half of a parabola, namely the right-hand piece, correct? To parameterize it, how do you parameterize it? Well, you need to have x and y as functions of time. So what should we do? And a very neat way of parameterizing the graph of a function is to just let the x-coordinate be time itself. In other words, let's take x to be t. So we're just going to set x equals t. Why? So we're going to say, well, at time t, the x-coordinate will be that same time t. So at time 0, the x-coordinate will be 0. At time t equals 1, the x-coordinate will be 1. And what's the y-coordinate? Well, y has to equal f of x. So y, in this case, will just be f of t. And f of t is, of course, t squared. So the general case, we just stop here, y equals f of t. In this specific example, well, in this case, it's t squared. So notice, x is t and y is the square of the x value, whatever it is. So we have successfully parameterized the parabola. And t, of course, has to be in the interval I, which in this case would be the half of the real line. So in this case, it would be everything from 0 to infinity. So maybe we can say that equals everything from 0 to infinity in this case. Not too complicated. It seems simple to parameterize a curve y equals f of x. Just put x equal to t and y equal to f of t. So I think you are owed a picture of this. So let's take a look at the parametric version of this parabola. And at time t equals 0, well, x is 0, and therefore y has to be 0 as well, because y is t squared. So here we are at the origin. As time moves on, well, the x-coordinate is going to increase, and the y will be the square of the x-coordinate, so it's going to climb up the parabola, as shown over here. There it goes, shooting up to infinity. Okay, fun to play with this slider and watch this parametric curve move off to the right. Incidentally, who said I had to parameterize it this specific way? What I'm going to do is give you another parameterization. Meaning well, if I could type, I would be able to do it, but let's try again. Another parameterization. Wow. Let's see if I can, no, not characterization. My spelling checker didn't help me very much. Parameterization. That is correctly spelled, so too bad. My spell checker doesn't seem to like it. It wants me to write it as computerization, which is kind of crazy. Anyway, another parameterization would be, well, let's not take x equal to t. Let's change it to, I don't know, let's take x to be 2t, or 2t plus 1. Or maybe 2t squared plus 1. In fact, anything you like. Because whatever you take x to be, y has to be the square of x. Because y is that function of t. So y would be not t squared, but 2t plus 1 quantity squared. So y would be 2t plus 1 quantity squared in this case. And you get the exact same curve. The only difference is that this curve starts off moving slowly but really accelerates as t goes on, because x is accelerating with time. It's getting faster and faster and faster, so it'll be something like this. Instead of moving with a uniform time like that, I'm going to start off slowly and then accelerate faster and faster, and it'll go shooting up faster and faster. And it's the same curve. So unlike the case with functions, where if you have a different function, you will get a different curve. In the case of parametrized curves, you can have totally different parametric equations for the same curve. Here are two sets of parametric equations for the same half of a parabola. And that is important to know. And the reason for that is a parametric curve has more information than just the curve. It also tells you how fast the curve is moving. It tells you where the point is at every specific value of time t. So you can think of it as a curve with a kind of track. It's being tracked through time. And that's what a parametric curve is. So time to move to another example. This time, we're going to look at a circle, a kind of general circle, whose center is x0, y0, and whose radius is r. Now remember, for polar curves, it's very easy to do circles with polar coordinates, especially if the center is at the origin. Now in this particular case, it's not going to be at the origin in general, but in the example I've drawn here, it is at the origin. And then as time goes on, in fact, this is the picture of, remember, I'm calling time theta, because this is exactly the polar curve you've seen before. So it's kind of like polar curves. You can think of time as, instead of calling this t, I can call it theta, which is really the angle, but you can think of it as time also. So let's see what the equations are for this particular circle. So in this particular case, let's type in a special case. And the center is going to be 0, 0. Close my parentheses like a good person. Okay. And then we already know from polar coordinates, if we think of time as theta, then at time t, theta is equal to t. And so x is r cosine theta, y is r sine theta. Do you remember that stuff? And except now we're calling it t instead of theta. So x is r cosine theta, which would be r cosine t. And y would be r sine theta, which would be r sine t. And t goes from 0 to 2 pi, which gives you the whole circle. So this is nothing more than polar curve, really, with theta changed to t. So the parameter is now theta, or equivalently, it's t. Now, what happens if I want the center to move somewhere else? Then what do? I don't think I can move this one, unfortunately, but if I want the center to move somewhere else, then let's see what's involved in doing that. So I'm going to move the center and ask myself what's involved in moving the center from 0, 0 to x0, y0. Well, first of all, I can move it in two steps. I can first move it horizontally to x0 and then vertically up to y0. I can do it in two steps. The first step, moving it horizontally to x0, means I have to add x0 to the coordinates of everything in sight, because I'm adding x0 to the 0 that's at the origin, and that means I have to add x0 to every point on the circle, which really means I just have to add an x0 to this formula that's over here. So let's just put that in words. And by the way, if you move it vertically up, then you're adding y0 to the y coordinates. So moving the center involves adding x0 to the x coordinates to move it right, and then adding y0 as the y-coordinate to move it up. That's all you're doing. You're just moving everything by adding values to the x and y coordinates. Adding to the x-coordinate moves it to the right. If it's negative value you're adding, it will move it to the left. And similarly, adding to the y-coordinate moves it up. So basically all I'm doing is adding an x0 to the x-coordinate and a y0 to the y-coordinate. And here I have answered the question in example E. This is the circle of center x0, y0, whose radius is r. And this is, again, one way of parametrizing it, where I'm using theta as the parameter. I could have replaced t by 2t, or 2t plus 1, or t squared, in which case you wouldn't be going around the circle at a fixed speed. You might be speeding up or slowing down, depending on the equation you're using instead of t. Now, we've been talking a lot about starting with curves you know, and then getting them to parametric form. Can you go the other way? Starting with this equation, or this pair of equations, can I get x and y? Can I get an equation in x and y only? The equation of this circle. In other words, I'd like to eliminate the parameter t. If you can eliminate the parameter of t from these two equations somehow or other, then you would get what you desire. Let's put that on a new line so it looks nicer. So we're going to eliminate, how are we going to eliminate the parameter for this set of equations that we're staring at over here? How do you get rid of the parameter? You might be tempted to solve for t in one of them and substitute in the other one, but that'll be awful. You're going to get, first of all, you can't solve for t because you're going to get inverse cosines, and that depends on the argument, whether t is between 0 and pi, or maybe between pi and 2 pi. Complicated. Is there another way you can eliminate the parameter t? And what comes to mind is that if this was squared, well, it comes to, I guess, only a mind of a person who's been thinking about it a while, right? And if this is squared, well, cosine squared plus sine squared is 1, and t is gone. So if you could somehow get cosine squared out of this and sine squared out, and that's not too hard to do, take the x0 to the other side and then square. Do the same for y and square, and then add. So let's, again, first take the x and the x0 and the y0 to the other side. Like so. They've gone over to the left. Then just square and add both equations. And that will eliminate t for us, won't it? Surely it will. If I square this and add, I'm going to get x minus x0 squared plus y minus y0 squared, that squared, equals r squared cosine squared t plus r squared sine squared t, which is r squared times the quantity cosine squared plus sine squared, which is 1. Bye-bye t. T has gone. We have eliminated the parameter. And guess what we've got? We got the equation of a circle. X minus x0 squared plus y minus y0 squared equals r squared. The equation of a circle, center x0, y0, radius r. And that is exactly what we were after. So by eliminating t, we've shown that what we've written down here is indeed a way of parametrizing that circle. At least gives us a lot of support for our notion that we write. Okay? Now, let's rewrite this equation. Why am I going to do that? Because I just feel like it. So just for fun, we're going to write it a different way, the equation of a circle. I'm going to take x minus x naught squared plus y minus y naught squared equals r squared, and divide both sides by r squared. So basically, let's eliminate this middle step, which, because it's not necessary, we've now eliminated the t anyway, so I'm going to just do that. Okay, so that is I've got too many equal signs, so let's get rid of one of them. That's the equation of the circle. Divide both sides by r squared, and you get that. Big deal. But this kind of allows you, well, what if this r was different from that r? If that is the case, you get something called an ellipse. So what is an ellipse? What's the equation of an ellipse? And I'm going to write that down. The equation of an ellipse is almost the same as the equation of the circle, except the denominators here are different. So for the one, I might have a 1, an a, and the other one I might have a 2, or something like that. I have two different, the kind of the x radius, this distance, this horizontal distance, would be r, and the vertical distance would be s. So it's as though I'm compressing this, stretching it in some way, and instead of getting a circle, I will get some kind of ellipse. So let me see if I can modify this picture so you can see what it would look like. Okay, let's see what happens. Now what's happening? Oh, I'm getting a kind of ellipse. How did I do that? Notice that my x radius, as it were, would be 2. So a would be 2. And y, however, would be 1. So a would be 2 and b would be 1. If that's the case, you get this particular ellipse. If x naught and y naught are both 0. This ellipse is centered at the origin. And how do we parameterize it? Well, think of where the r's go in the parametric equations. The r from the x is over here, and the r from the y is over there. So this r is really the first one, and that r is the second one. So if I change one of them in the parametric equations, all I'm going to get is exactly the same equations, except with two different, instead of r, I have a and b. So I'm going to have an a here, and I'm going to have a b here. And that's it. Same, very easy. Now, for polar curves, it wouldn't be so easy, would it? Here's an exercise for you if you don't believe me that this is, in fact, a parametrization of an ellipse. And the exercise for you to do is pause the video and eliminate. Don't do that, I'm just repeating myself. Oops. The exercise for you is to eliminate t over here and obtain the above equation. Reobtain this equation, starting from here, doing the same procedure we did to eliminate t, squaring and adding, but this time you have to first divide, subtract x naught, divide by a, subtract y naught, divide by b, then square and add, and you'll see it'll work. Something for you to do, pause the video and do it. And once you unpause the video, we can get back to doing example G. Example G is, again, a kind of general example. We saw in the kind of third example how to parameterize any graph of a function of x, y equals a function of x. Now we're going to parameterize, I should say, a polar curve. R is a function of theta, and theta, I could mention theta would be in some interval. So for example, theta would be in some interval I, as shown over here. So then you get a polar curve. Well, we do just what we did in example E of the circle. We just replace theta by t. That's the easy way of parameterizing it. So the answer is just do what we did in example E. In other words, replace theta by t. Now, how do you do that? Well, x is r cosine theta. Now, there's thetas occurring in two places. because now r is not fixed anymore. It's not a circle. It's a function of t. Depends on t, or depends on theta. Remember, in general, we had r as a function of theta. And theta is now t. So it's going to be r of t instead of r of theta. It's r of t. And multiplied by cosine t. And y would be r of t, sine t. And t would be in the interval I. So t is in the interval I, which I'm just adding in there. So let's try an example. For example, the cardioid, our favorite, or not so favorite, polar curve. The cardioid, remember, is r is equal to 2 times 1 plus cosine theta. At least that's one of them. How do we parameterize it? Well, we take theta to be t, and then we just write down these very same equations, except using the formula that we have for r instead of r of t. So r of t would be 2 times 1 plus cosine of t, as shown here. Here is r of t. 2 times 1 plus cosine of t, and then just copy the rest of it over. Same for y. So this would parameterize what we wanted. Now, I have not done a kind of picture of it. Maybe I should. So let's see if I can get a cardioid for you, and that will be the last thing I do in this video. Okay, I did it. I paused the video and changed the parametric equations to these. And t is going from 0 to 2 pi, and let's see it go from 0 to 2 pi, and there's the cardioid. Okay? Familiar curve to you. And those are all the examples we're going to be doing for now. You will see others in the homework. And in the next video, we'll talk about doing things, doing some calculus, like calculating the length of one of these curves as we did for polar curves, and also the slope of the tangent as we did for polar curves, except we'll do them for parametric curves. So see you in part B.